Live. We are live. Okay. Let's see here. Okay, so I think this is posted everywhere. Still no viewers. Okay. Give some people a chance to show up. Oh, got some people. All right. So we're going to start with usual, like usual, with the $10 and up questions. And then see if I can hunt down the live chat again. It's always so difficult to find. All right, let's see here. Let's start with, we're back down to 0 viewers again. Let's see here. Actually, let me just see if I can find the chat. Anyway, oh, yep. Got that open, so that's good. Save that for later. All right. So let's see. Got a question from Timothy that says, ever notice how similar this relationship is to the Pythagorean theorem? That is, E squared equals MC squared plus, it's the relativistic thing that relates momentum, mass, and energy, which shows up a lot of different places. It's considered one of it's sort of the generalization of E equals MC squared. And he points out that it looks very similar to Pythagorean theorem, and he wants to know if there's any significance to that. And yeah, that's not a coincidence. In fact, I can help with this if I can figure out how to share my screen here. I think can I really? Okay, fine. We'll share the full screen. Ooh, infinity. Okay, so right here, I'm not sure if you can see this, but it looks like you can. Okay, so this is my ebook. Some of you probably already have it, but underneath, is it showing the browse? Is it showing the cursor? It is. Okay, good. So underneath special relativity, relativistic dynamics, and four momentum, that's four-dimensional momentum, just sort of shortened. Basically, there's this concept called four momentum, which is just an example of a four-dimensional vector. It has four components. That's three components for space and one component for time. It's a very common way to represent things in relativity. It makes things very convenient mathematically. But basically, there is this thing called four momentum, which basically is the three-dimensional momentum plus a time component. And if you take that, right, if you take that and you square it, which is usually what you would do if you're doing Pythagorean theorem and you're trying to figure out the length of the side of the triangle, right? You do a squared plus b squared equals c squared. Well, a and b are the two directions, and the c is the total vector. And so in this case, if you sort of take the three dimensions of space and compress them into one, you basically just get one space component and one time component, just like you would have an x and a y in a triangle, right? And so if you then square that, which you would do to get, this looks very, very fancy, but it's basically just p squared. and P is momentum. And so when you do that, right, that's like saying C squared in the Pythagorean theorem, and then you just need to figure out the other two components. Well, the other two components are here and here. They relate the energy to the the three-dimensional momentum. And so when you actually work that out, what you end up with is exactly the relationship that Timothy was bringing up before. And that is energy squared, and then you've got m squared c to the fourth, which takes care of the length of the side, the diagonal side, and then the other component, momentum squared times the speed of light squared. So you get a relationship between energy, mass, and momentum just by doing exactly that, doing Pythagorean theorem on four-dimensional space-time instead of three-dimensional space or two-dimensional planes or whatever. And so this is exactly how you get that relationship. It is not a coincidence that it looks just like Pythagorean theorem, because that's how we get it. Okay, so unshare screen. How do I undo this? Stop screen sharing. There we go. Okay, so we're back. Let's see here. What do we got here? That's not what I want. All right, so next question we've got here is from Vittorio. I don't know if I'm pronouncing that properly. He actually asked several questions, but we're just going to stick to one for now, and I'll come back to some of these if there's a low in the conversation later on. But first question here is, well, I guess we'll go with one that's a little more scientific. What is the false vacuum decay? Is it a real thing, or is it just a mathematical trick? It's not. I wouldn't call it a mathematical trick. It's sort of a mathematical consequence. Basically, I keep bumping the table. Basically, in quantum field theory, there is this thing called the Higgs field, which everyone gets very hyped about. It's very exciting, right? But see, the problem is that most of these fields hover around, and I say hover, but I mean, like, it's basically just sitting there with some uncertainty. Maybe instead of hover, maybe a better word would be hum, because at least that way we're sort of referring to some kind of wave thing, right? Referring to sound. But they kind of just hum a little bit at around zero energy, sort of their ground state, right? And then if you excite any of those positions, you get a particle. Now that's going to be true of the EM field. You get a photon. The electron field, you get an electron or a positron. You get options. But that's only when you force one of the fields to be at a higher energy. Otherwise, it's going to be sitting at around zero, and you basically get no particle. But the thing about the Higgs field, in order for it to actually work the way that it's supposed to work and actually give things mass, the entire field overall, like the entire stretch all the way across space, has to hover or hum higher than the ground state, to higher than zero, right? We would typically call the ground state zero. And so it doesn't actually sit at its own ground state, which is a very strange thing to have. I might be saying this wrong, but the point is it hovers, its value hovers above where we would expect it to be if it was, resting, I guess, at equilibrium. And so it's got all this, it like maintains a certain amount of energy above all of the other fields that exist in the universe that give us all the other particles. And so it seems pretty stable. I mean, the universe exists and it's existed for a long time. But the problem is that theoretically speaking, I guess I should say hypothetically speaking, there could be a place in the universe somewhere where the Higgs field drops down to the zero level, drops down to that ground state with all the other fields. And if it does that, that point where that happened could cascade and start to affect the other like points around it. And that drop can spread across the entire universe. And as that happens, basically all the other particles in the universe, all the other fields will lose their rest mass and sort of cease to behave the way they normally behave. And the way they behave happens to be the reason that things like atoms and chemistry and all this stuff, everything in the universe exists. And so if it drops down and spreads away, which it would do with the speed of light, then it would basically destroy everything we consider to be the universe on that level, right? Everything that at least we classically consider to be the universe, stars, planets, people, all that stuff would just disappear. Now, that would take some time. So if this happened on the other side of the universe, it would be a while before it got to us. But we wouldn't see it coming, because if it's traveling at the speed of light, that is the maximum speed at which any information from anywhere can get to us. And so if that sort of shockwave in the Higgs field eventually hit us, it would hit us and we wouldn't see it coming. And so it would happen pretty fast. We'd be here one moment and then the next moment we'd be gone. But the fact that that hasn't happened yet, right, in the tens of billions of years that, I should say that just the 10 billions, the 13.8 billion years or so that the universe has been around, leads us to think that it's not something that's easy to do. That if something like that did happen, it would have to be some like malicious alien race or something, or we did something stupid. But I don't think stupid would cut it, right? Because if something happened accidentally, there's no reason it shouldn't have happened accidentally naturally. And so we'd have to like make a conscious choice to do something like this. I don't think it's something that could just happen. And other scientists don't either. So while it's hypothetically possible that the Higgs field could collapse to the ground state, which we call the false vacuum collapse, it's not really anything. It doesn't seem to be something that we really have to worry about. In fact, we could end up discovering something more fundamental, some model below the quantum field theory, and it will show us that that's not actually possible. But for the time being, it is a possible concern in quantum field theory. So it's not something that's just a mathematical trick. It's not something we're playing with the math and then we came up with this thing that's going to like get people excited or scare people or whatever, and then have it not be a thing. It's something that is actually technically possible, but I wouldn't worry about it. Okay, so let's I guess open up the chat. Looks like some people are already asking questions. That's great. We've got let's see how many places I have to check for things. Okay, so we've got a question. How are the vectors in a gravity field measured and defined? Okay, so this is another reason that we use four vectors or four-dimensional vectors in space-time, is because they're easier to define. We can define them in terms of their own rest frame. Because all of these vectors, all these measurements, they're going to be attached to some kind of object or particle or something. And so that particle should have a rest frame unless it's a photon or a gluon. But most particles have their own rest frame, and we can define all of these things like for position and for velocity and for momentum and for force. And we have all these names for four-dimensional versions of our vectors. But they're really convenient because we can define them like sort of outside of any curvature we might see in like a gravitational field, right? And so at that point, things are a little easier to work with. And once we have that, you can transform it into a frame of reference where there is a gravitational field or whatever, where the particle they're attached to isn't at rest. And that's fine. A lot of times we have to do that. We want to know what those measurements are in our frame of reference instead of the particles. This is a very common thing. But we don't have to define them in our frame. We can define them in the particles frame or in the object's frame, and it's a lot easier to do. Okay, so see, relativity question. To accelerate a frame so it does not break, it must be accelerated uniformly, for the clock at the back must lag behind the clock at the front. Okay, so I guess, yeah, so technically speaking, if you are in, say, a rocket, right? So if you're in a rocket for some time, right? You have the situation where, like, if the rocket's at rest and you ignite the rocket fuel in the back so that the rocket's getting pushed forward, the back of the rocket is going to move a fraction of a fraction of a fraction of a second before the front of the rocket does. And so that could be the case, right? That the back of the rocket is moving, and if you got a person back there and a person at the front of the rocket, then their clocks will at least, momentarily disappear. Actually, momentarily disagree, right? But then once you get up to speed, you sort of like level off. But if you continuously accelerate, you could have the back of the rocket be at a slightly different time speed, I guess you could call it, than the front of the rocket, which I don't know that that's necessarily a problem. I've never heard it called Bell's spatial paradox before, but I'll look into that. But I don't know that that's really a paradox that the two disagree. I mean, that just means that they're like, it's okay for people to disagree in relativity, and there's no right or wrong there. But I mean, I don't know if some of that causes other problems, but it kind of makes sense, right? It kind of makes sense that the rocket at the bottom would at least, if it's moving faster, it's going to have more special relativity time dilation. But I'd have to like really sit down with the math to decide whether or not like the gravitational field that's created or the fictitious one that's created there would cause some other problems. But think about an 8 light-year long rocket. Yeah, I don't know. I think, see, the problem with hypotheticals like that is that you can't really build an 8 light-year long rocket. I don't know if any structure in particular that's 8 light-years long. I mean, not a solid one anyway. There's a reason that they're sort of limited in size. It's because other factors kind of tear them into pieces. It says if you accelerate 2 points at the same distance, accelerated at the same proper acceleration, will break the frame. I don't know about that. I mean, I don't think that that you're necessarily breaking the frame. I mean, there might be some kind of like frame gradient from the front of the rocket to the back of the rocket, or vice versa. But I don't know about breaking. Let's take a look here. Else spaceship paradox. Widely known as is included in modified version. This is the rope, the string one. Sure. Right, but I think ultimately, I'm sure there's a solution to this. There's got to be a solution to this, but because paradoxes don't actually exist in the real world. But yeah, I mean, I'll look into this. I'll keep the tab open and look into this later. But I've heard of the string attached between the two rockets problem, involving like the distance between two different rockets that are separated by distance. I think at one point I considered including it in the ebook, and then I had enough paradoxes in there that I kind of decided against it. Got a little obsessive with the twins paradox, as I do. But there is some give, like I think a lot of this probably assumes that there is a perfectly rigid string, which doesn't really happen. And so like I think when people come up with the paradoxes like this, right, and they call them paradoxes, and we try to sit down and like figure out why they're there, you have to remember, right, and I say this several times in my videos, that like a paradox isn't really a thing. It's not something that exists in the universe, right? So you think like Back to the Future, and Doc Brown is like, oh, we're going to create a time paradox. It's not how the universe works, right? The universe is a very stable, very structured thing. It can outsurvive us, right? We're not going to destroy it just by traveling through time. That's ridiculous. And so a paradox is usually something that is stuck in the math, right? It's something that we've like sort of arrived at when we're doing math, and what it usually means is we've made a mistake, right? There are two options. Either we haven't considered everything we should have considered, right? Which is usually what a lot of these fancy paradoxes are, right? They're a problem where like someone has made too many like extreme assumptions, like the string doesn't have mass, or it's perfectly rigid, or something like that, and you can't actually assume that in this particular scenario, right? You can only make assumptions like that some of the time. You can't make those all of the time. And so that's one. The other option is that our model is incomplete, which does happen periodically, but it's usually the first one. It's usually we're making some kind of assumption we shouldn't be. And so I'm sure this Bell spaceship paradox is in the same category. Okay. So let's see here. Related to the electricity flow video, right? So I just put out electricity flow video. Could you elaborate on the skin effect? Kind of left it hanging there. Yeah, I didn't want to. I mean, the video was already getting too long, and if I had gone into detail about the skin effect, it would have just sort of detracted from everything else. I didn't want the video to feel like I was just dumping a bunch of little facts into it, right? That wasn't what it was about. It was just about whether or not the current actually flows. And so with that, I had to point out some differences, right? Every analogy, I was using an analogy of water in a pipe, and every analogy has its limits. And so I was trying to at least point out some of the limits before I finished up the video. And so I kind of just tacked the skin effect on there at the end. But the basic idea there is that in the center of the wire, right, there's kind of a bit of a drag on the actual current that's flowing through the wire, the whole collection of electrons that flows through. And so, I mean, I could go into a whole video about it, but basically, there isn't as much room to move around in the middle of the wire as there is on the edges. And so as a result, if you have a voltage that's pumping some current through a circuit, through some conductors, then the current on the outer edges of the wire are going to be, the charges on there are going to be moving a lot. I wouldn't say a lot, but they're going to be moving faster than the ones in the middle, or at the very least, there are more moving charges on the edge than there are in the middle. Not necessarily at a different speed. It's, remember, current isn't really about speed. So there are more electrons that are kind of free to move around near the edge than near the center. Now, it doesn't mean that the ones in the center of the wire don't move, because they do, if you give them enough time to, which is what DC does, right? If you've got a voltage that's always pumping current the same direction, right? It's always going the same way, then the charges in the middle of the wire do move, right? They do sort of overcome this resistance a little bit and move forward. Not as much as the ones on the edge, but they do move forward, which the animation kind of showed. They were moving kind of slow near the middle, but then really, really fast to the edge. And so in DC, you still get a flow through the entire volume of the wire. It's just they're going a little slower in the middle. Whereas with AC, the voltage flips back and forth, right? It flips back and forth, and so the current moves back and forth. And because it's continuously changing like that, the charge in the middle doesn't really have time to sort of overcome that, right? By the time it overcomes the resistance it has to move forward in the direction the voltage wanted it to go, the voltage is already pointed the opposite direction. And so in that time, the charge just kind of just sits there in the middle and it doesn't go anywhere. And so you basically only get a current on the sort of edges of the wire, not the absolute edge. There is a thickness to it. In fact, I'm going to pull up a diagram. There's a diagram of this. Okay, so I'm going to pull this up in the Wikimedia Commons here. I'm going to share the screen again. And so right there, we've got a diagram, right? And so that delta symbol, let's go over there. That delta symbol right there is sort of the width of the thickness, like how thick the skin is, right? It's called the skin depth. And so you can see that the darker spots are where there is more current flowing, and the whiter spots in the middle are where there's basically no current flowing. And so that is, you can see it's a gradient as it moves away from the middle of the wire, right? This is just a cross section of the wire. So you get a lot more current near the edge and not so much near the middle. Now in DC, that dark spot does get lighter as it goes in, but it goes all the way into the middle. Whereas with AC, you get this empty patch where there basically isn't any current at all. And so you end up with this sort of skin current around the edge. I don't know if that answers your question enough, but there's a lot of factors that go into how the current actually moves in the conduction band, how it jumps from atom to atom in that band. And so because there are fewer atoms around the current on the top, on the edge, right, on the outside edge of the wire, there's less resistance there. There's less influence for the charges. And so they can just mostly go wherever they want to go. Whereas the deeper in you go, the more and more atoms there are on the top and the bottom, like around the charge, around the electron, and so it has a lot more influences in the middle than it does in the edge. Higher frequency, thinner skin, yes, definitely, because as I was saying before, the charge near the middle of the wire has a really hard time catching up. And so by the time it tries to move one direction, the voltage is already trying to tell it to go the other way. And the faster it switches back and forth, right? I mean, that's just here in the United States, it's about 60 hertz. So the voltage switches back and forth 60 times a second. And it's fast, right? But there are ways of generating higher frequencies, right? You just need a AC power source, and you can adjust. It's called the function generator, and you can adjust the frequency. You can take it up to like 2,500 hertz if you want to. And the higher the frequency, the harder it is for the charges to do what the voltage is telling it to do. And so you get a thinner and thinner skin on the wire as the frequency goes up. Or switch mode power supplies in your computer. Yes. So there are some applications where you need it to be a different frequency than what you're plugging it into. And so you can adjust it, right? You can adjust the frequency as needed. It doesn't come up everywhere, but it does come up in certain places. That's why a TV antenna is hollow. Yeah, that makes sense. It's also cheaper to make a hollow antenna. But and plus, if they're hollow, then they're more fragile, and then they break, and you have to buy a new one. Capitalism. That's how it goes. So that's the basics of that. Let's see. Higher frequency, more internal stresses, more friction due to heat. Yeah, there are a lot of, like I said, there are a lot of factors with how these charges move through a material, right? I mean, they go up to the conduction band, but over time they lose energy and they can drop back down. And there's a lot of stuff going on with individual electrons that we don't really worry about too much when we're just doing basic circuit stuff, which is kind of what I'm doing in my series right now. We just kind of clump it all together, take an average, and we say, okay, well, then there's just a current running through the wire, and that's it. And we move on, and we don't worry too much about the sort of like material electrodynamics, the actual material science that goes into that, because it's not always important. All right, so let's see. Do you see anything here? Let me go back to some of these. Have you tried Universe Sandbox 2? What do you think about it? I have not actually tried it. I mean, I've seen it before. I have I don't know if you know Toby. She does physics videos. It's very, very soft spoken. Tibbies, Tibees. She's played around with it a little bit before in video, and I actually was always sort of surprised where it was in a video, but I actually checked on the usage rights recently, and they say as long as they're attributed, you can totally put them in a monetized video and it's fine. And so I'm totally buying this thing. It's like 25 bucks or something, but I'm very excited to get it and try it out and see how it works. It might actually save me a lot of time when I need to do a astronomical animation and I don't really want to go through the trouble of making one. I don't have time or whatever. I can just pull up Universe Sandbox and credit them for 2 seconds and I'm good to go. And so I'm very excited to try it out. It's unfortunate that Universe Sandbox doesn't do relativity. but that's basically impossible without a supercomputer. So I can't get on their case about it. It's just kind of a downside. It is 100% Newtonian. I mean, I guess 99.99% Newtonian, because you can technically turn things into black holes by changing their radius, but you can't figure out like what's happening with like time and space near the black hole. You can just see what a Newtonian black hole would do, and that's basically all it is. It's not a relativistic black hole, but it's very cool software, very well designed, and so I'm excited to play around with it. Does the current flow pick up other properties similar to water too? The skin effect sounds similar to surface tension. Can eddy currents build up in wires too? There might be. I mean, you can get eddy currents, but they wouldn't necessarily happen on their own. I mean, there are such thing as electric eddy currents. They happen a lot, especially with magnetic induction, which is a video that's coming up in probably mid to late January. But so they can happen, but they don't normally. You kind of have to it's another effect that actually causes it. But there are some other effects that happen inside of materials that involve current, right? So when we say current, what we usually mean by that is a free current, a current that flows from one place to another in a wire or a conductor. But there's also something called a bound current, which is it's a little different. It's not something we normally would consider, but it is something that if you're doing advanced electrodynamics, you kind of have to consider. And so, because normally what we do is we assume that a material like copper is just it's a conductor. The charges can just freely move through it, no problem. And sure, it's got a little bit of resistance, but we don't worry about it too much. But when you're doing fundamental material science, you have to consider the fact that no material is a perfect conductor or a perfect insulator. And so as a result, on top of any free current that you get moving through something like a copper wire, you can also get these little tiny currents that add up, that can add up sometimes to something large. But they're called bound currents because they don't actually go anywhere. They kind of just circle around and cycle through. And so overall, they don't affect a whole lot in your circuit, but they do affect the behavior of the material, and so you have to sometimes consider them. So they do kind of happen, right? There's other little details in material science, things that do happen, but they're not things that we normally have to worry about. Certainly not when you're designing a circuit. But if you're trying to fundamentally understand what's happening, sure, you should probably consider stuff like that. Is electricity current affected by gravity at any scale? Well, I mean, everything with mass is going to be affected by gravity. I mean, technically anything with energy is going to be affected by gravity. And so, yes, technically speaking, electricity is affected by gravity, but the problem is that the current is, if we're talking about current in wires, right, that the charges that are actually in that current don't make up a very significant portion of the mass in a wire. And so the gravity will, no matter how much current you have, like the gravity's always going to be affecting the protons and neutrons in the wire way more than it is affecting the electrons. And so it's never going to like pull the electricity off the wire it's just going to pull the whole wire, right? I mean, it's kind of what gravity does. It just pulls the whole thing, and sure, the current is going to go with it, but that's about it. Now, if you've got some kind of plasma, like a star is made of plasma, it's just a bunch of charged particles, and those charged particles are moving around in currents, which is exactly why the sun has a magnetic field, because moving charges make a magnetic field. Then sure, I mean, if you've got something that's independent of like an object, right? If it's some kind of current, some kind of motion of charge that is just flowing through space on its own, then yeah, I mean, gravity is going to pull that in because it has mass, just like it's going to pull anything else in. That black hole is going to, for example, a black hole will gobble up a star, and that gravity is definitely affecting the way that the charge moves inside of that star. And so technically yes, but I don't know if that's what you were envisioning. Maybe not, but black hole versus electricity, yes. Black hole wins every day. Drake, you having a little trouble with the messages there? So yeah, let's imagine that it's part of a where we will measure a stronger current. I mean, if your gravity was strong enough and your wire was strong enough and you like dangled it down, like if you dangled a wire down to a black hole, but I don't know how you would. Man, I have to sit down with this because, like, if you had a really really long circuit, like you just had a wire that you dangled down to a black hole and then wrapped back around to your battery, right? You just hooked the battery up to a big long wire, and you dangled this super long wire down into toward a black hole. What would happen to the current? I imagine that if you somehow had a wire that wouldn't be torn apart by this black hole, that the current would go faster on one side and slower on the other, at which point it would probably build up at the tip, the edge that's closest to the black hole. That'd be interesting to like sit down and see what would actually happen to the charge that builds up at the end. I've never thought about this before. This is a very, very interesting idea. I think electrons are lighter than photons, hence why they're using lasers to measure gravitational waves. They're not. I mean, but at which point, like, you got to consider what you mean by lighter. I mean, if you're talking about rest mass, the photon wins every moment of every day, right? Because there's no rest mass in a photon. But I mean, in terms of just overall energy, like relativistic mass, which is what you need to worry about if you're talking about gravity anyway, affecting a black hole or affecting a photon, then sometimes the photons can have more of that, right? Sometimes they can have more energy. There are a lot of gamma rays that have more energy than a single electron. That's not impossible. But I don't know if that's the reason that they use it. I think it's just a lot easier to use photons because they're not affected by a lot of things. And so when you're trying to do some very, very fine measurements like they do in the gravitational wave observatories, you want to be using something that isn't going to be affected by much else other than a gravitational wave passing through. And so you want to try and rule out as many like sources of error as possible. And so photons get used because they're electrically neutral and they don't have any rest mass, and so they're very easy to use and they don't bring in a lot of error with them. Whereas if you used electrons, they're charged, right? A stray magnetic field can affect their direction, right? There's a lot of other things that you'd have to consider, which you don't have to consider with photons. So photons are a very, very nice way of trying to, measure things, which is why we use them a lot in quantum measurements. What is the maximum energy a photon can have? Well, that depends. At the moment, there doesn't appear to be any maximum energy that a photon could have. But if in order for there to be a highest energy, there'd have to be a highest frequency, like you said, but the only reason that would happen is if there's a minimum wavelength, at which point we're back to Planck length. And I've mentioned before that we don't have any evidence that is physically significant, right? That there's actually a smallest amount of space. And even if there is a smallest amount of space, it doesn't guarantee that it's going to be Planck length, but that's sort of the running hypothesis, right? The idea is that there might be. And so if there is, right, if there is a minimum amount of space and it is the Planck length, then the minimum wavelength that a photon could have would be the Planck length, and that would determine its maximum frequency and its maximum energy. But otherwise, there is not any limit. There's no upper limit to it. You could eventually have a photon that had the energy of, say, an asteroid, equivalent to the rest mass of an asteroid, which is crazy. And frankly, that photon wouldn't last very long. It would just kind of, decay into other particles, probably a whole bunch of other particles. It would last a very, very short amount of time, but it could theoretically exist. One last question here. Can we see? Let's go back up here. I kind of missed a question. Since sound pressure waves affect particles creating motion in the direction of the wave, does then sound perpendicular to a wire increase the resistance? I've never seen anything done on that. I'd like to see an experiment. But I doubt it, because again, just like the gravity, I think the sound would affect the entire wire. I mean, it's not going to necessarily affect the protons and neutrons more like gravity does, but I mean, it's possible that there's a negligible effect, but I've never seen an experiment done on that. I have to look into it, but I guess it's possible, but unlikely. Let's see. Can we accelerate a particle to be a black hole? No, we cannot. And there's a few ways to. Oh, go back. Yeah, okay. So there's a few ways to look at this. So first, the most common explanation is that black holes are just created by rest mass, which I don't really like, because that sort of negates the ability of photons to make a black hole, which they can do that. But the better way to look at that is to say that, I think I said this in the Making Black Holes video. So where the motion of the particles that make up something, that make up an object, can contribute to the black holeness of something, right? Its ability to be a black hole, but not the motion of the whole object. And so I think the sort of the simplest way to say that would be to say that And this is what I said in the video, that like, in order for a black hole to be created, right? Just like with anything in relativity, you need the black hole, the event horizon must form in every frame of reference, including the reference where the black hole is stationary. Or I guess including where the source of the black hole is stationary, right? So whether it's a neutron star or an individual particle or whatever, right? You have to consider the fact that the event horizon, which signifies the formation of a black hole, that has to form from every single person's point of view, everywhere, right? When events occur, everyone agrees that they occur. They might disagree on what order they happen in, or how much time passes between them, or how much space is between them, or some stuff like that. But everyone agrees that the event happened. And so the formation of the event horizon, everyone's got to agree on that. It's a thing that happens. And so it has to even happen in the rest frame of this hypothetical particle we're talking about. So no matter how fast you make that particle go, and how much kinetic energy you give that individual particle, it doesn't matter. Because if it's going to form a black hole, it's going to do it in the rest frame of that particle too. So like, let's say it's a proton or something, right? So you're accelerating a proton, you're making it go faster and faster and faster and faster as you approach the speed of light. There is a frame of reference, a point of view where that proton is stationary, and the black hole has to form in that frame as well. And so in that frame, it doesn't have the extra kinetic energy that you're talking about from accelerating it. And so it doesn't form a black hole. And so like, I guess so the best way, if you want to use an equation like the Schwarzschild radius to calculate how big a black hole will be, or whether or not a black hole will happen, you have to remember that equation, the Schwarzschild radius equation, is derived in the rest frame of the object. The object is not moving around, and so it doesn't take that into consideration. If it did, it would be a different equation, at which point you wouldn't get a black hole. So when you're considering black hole formation, I guess the easiest way to handle that is to just do your calculations in the rest frame of the object or particle. And so, no, the answer is a very definitive no. Drake says, actually, there is a problem in electronics called microphonics that affect electronics with sound pressure. Ooh, that's cool. Usually in radio frequencies, very sensitive circuit. Yeah, receivers are sensitive, aren't they? Oh yeah, right. Because if they're receivers, or if they're like radio filters or whatever, then that's frequency dependent. You have to tune those things, and so I guess that makes sense, right? If you're dealing with AC in particular, right? I don't know that it would have an effect on DC, but I guess in AC, if you're doing very specific applications, it would affect. It's anything that's frequency dependent. If you send a sound wave in, it can tweak the frequency a little bit, and a little bit might actually be enough if they're very sensitive. So thank you, Drake. I hadn't considered radio circuits, so this is what I get for taking questions live. It's a bit scary. How can photons make a black hole if they can have no limit of energy? Because the problem is not the energy, right? The problem is the size, right? In order to make a black hole, you have to get a certain amount of energy into a small enough space. And that's the problem you're going to have if you try to make a black hole from a single particle or even a single photon, right? So if you try to do that, right? If you try to have a photon with the energy of whatever, of the rest mass of something, equivalent to the rest mass of something, one, it's not going to last very long, and two, you have to localize it into a small enough space, a space smaller than the Schwarzschild radius, right? Uh, that's not something that you can do with a single photon, but you can do it with multiple photons, right? So if you have multiple photons, you can put them into one place, even two ought to do maybe, but usually it's going to be better if there's a bunch, right? So it's going to be a lot easier, that's for sure, if there's a bunch. And so if you can get a bunch of photons with a normal amount of energy into one place, it'll turn into a black hole just like anything else will. But getting one particle to do it is not going to happen. Because you have to be able to localize its position with a certain uncertainty in a certain space, right? And you can't do that with a photon. It's not going to happen. You could do that with an electron, for example, right? So if you use some light to localize an electron that happens to have a lot of energy or even a normal amount of energy, if you do it enough, if you localize it enough into a small enough space, it could potentially turn into a black hole. That's not easy either, but it's not technically impossible. So I can't really rule it out. But you're not gonna accelerate a single particle and turn it into a black hole. It's not how it works. Do antiphotons exist? Yes, they're called photons. The photon is its own antiparticle. And so all it has to do is just have an opposite spin, and it's an antiphoton. It's got no rest mass. It's got no net charge, right? All it's really got is spin and some energy. And so there isn't a lot that you have to worry about in terms of antiparticles for photons. So they can annihilate themselves, right? They can just, two photons can come together, and if they got opposite spin, boom, they're going to annihilate and turn into some particles. All right, so let's see. We're running out of time here. I got some more questions somewhere. And double check all the places. No comments there. Comments there. No comments. Comments? No. All right. So one more about the wires, I guess. Lots of questions about my electricity flowing video. Says it's in reference to the flashlight animation. When we close the switch, it says the electrons near the negative pole will be the first to move with drift velocity. Is that right? Well, that was a question. Of course, with all things considered quantum mechanically, I think there was a question in there. Oh, will they be the first to move? Probably. Well, okay. So I guess as far as these are concerned, right? I mentioned that the charges kind of like all move together, but technically, right, because the electric field doesn't like actually propagate through the wire instantly, right? It takes some time, some significant fraction of the speed of light, probably not exactly the speed of light, because it doesn't travel at the speed of light through materials necessarily. That they sort of like, and I had a lot of commenters mention this, that if you've got one that like moves like this, then it bumps the next one, and then like they just kind of do this. But I mean, eventually they kind of just reach an equilibrium and all just move together. But they're all already moving, right? They're all already jiggling around. It's just the drift of them that gives us a current. And so it's kind of hard to think about individual charges, individual electrons, but I mean, they do flow away from the negative end of a battery, but I don't know if, I mean, you could say that a whole clump of them, the drifting starts at the negative end of the power source, in this case, the batteries and the flashlight, they do start there some very, very small fraction of a second before the ones at the switch or the ones at the light bulb. But in the end, it doesn't really matter. But yes, technically speaking, the charges at the battery, at the negative end of the battery, will start drifting first. And then they kind of nudge the ones in front of them and nudge the ones in front of them. But that nudge happens all the way through the wire very quickly. And so then they all kind of start to move. They all nudge each other with electric force, which is related to the electric field, which is what I was talking about in the video. And so the two explanations are the same. They're very similar explanations. They're explaining the same thing. So they're both right. And so I guess to answer the question, yes, technically the ones at the battery will move first, but effectively it doesn't really matter. They all basically just move together. It's not really important to worry about which ones are moving first unless the flashlight is also, the whole flashlight is also moving at some fraction of the speed of light, like 50% the speed of light or something. At that point, you have to worry about whether or not, the charges near the battery move before the ones at the light bulb or the ones at the switch. But otherwise, unless that's happening, if you're just holding the flashlight in your hand, it doesn't matter. It's so fast that it doesn't actually matter which one moves first. Electric force, electric fields, inductance in there somewhere. Yeah, so there's a lot of jargon that we throw around in electrodynamics, right? There's a lot of words, and I try to use them as sparingly as possible in the videos because they don't necessarily add anything to the conversation. But I do have to use them sometimes because I have to refer to something in particular. But even then, when I do it, people still get it confused. Like I'm still getting comments on my current video about the difference between like an electric field and electric current. And it's not that they're confused about the difference. It's that they didn't like catch that I mentioned the electric field because, and that's fair because it's the only time I mention it in the entire video. And so I can understand why people would like entirely miss it. Right. And so the questions are usually like, wait, how can you say that the current moves at the drift velocity, but then also moves at the speed of light? And so there was some confusion. I probably should have stretched that part of the video out a little bit. But yes, there's a lot of terms, a lot of things to keep track of, right? There's electric force and electric fields and electric current and electric potential. And there's a lot of different measurements that we take for electrodynamics, electricity, and magnetism. And so it gets very difficult to keep them straight sometimes. But and that's why I try to only use them when I have to. If I don't have to, I'm just not going to mention it. Or maybe I'll just include it as text on the screen instead of saying it out loud. I've been known to do that. So that's going to actually happen a little bit in my next video because I'm already mentioning too many words. Like I'm already talking about like elements on the periodic table and stuff. So it would be way too like jargon heavy if I mention them. But yeah, these are things that we have to sort of keep separate. If you want to know what electric fields are all about, you go back to my what is charge video, and I basically explain them in there. So that's where you're gonna find those. Okay, I think we had a low turnout today. Maybe a lot of people that want to watch this are living like on the other side of the planet. I guess if you're watching this now and you're seeing it later, when we close this, just comment on the actual video that gets posted because this is gonna post as a video for later viewing, and feel free to post, like, I guess what your time zone is, so that I can get an idea of, you know, who's watching this and what times there are. Maybe we can like come up with a more convenient time. But otherwise, I don't know what else to do. Okay, so we've got that. I don't think electromagnetic waves, then into photons. Yeah, it's a lot of, there are a lot of relationships with that stuff. And I mean, like, this whole electrodynamic series is going to kind of culminate in electromagnetic waves, but it might be a while before we get there. I'm getting kind of burnt out, and so I might start like mixing in other videos that I want to do in between, some other videos that I'm very excited about working on, and I want to sort of sneak those in. Yeah, electrical engineering. It's very exciting for me too. I mean, it was kind of before I discovered relativity. I was into electrodynamics. It was very fun for me, and so whenever I teach classes and I teach the sort of second course where you get into electric fields and magnetic fields and light and stuff, it's always very exciting for me to teach that class. It's stuff that I get really excited about. So, all right, I think we're just about done here. It's been about an hour. So, thank you all for coming, and as usual, about a week before the next one, I'll post. But this last Saturday of the month thing's been really working out. I've been enjoying it. 68 minutes. Yeah, 68 minutes. That sounds about right. That puts it right in the line of the last 3 or 4 live streams. So, yeah. So last Saturday of every month we'll do this, and about a week before I'll make sure I put out the post on Patreon for the preliminary questions and things. But on that note, thank you for coming today, and it's been a blast, and I will see you next month. All right.